Welcome everyone. So this is the second season of our JetBrains coding club. So in this club we're solving problems and discuss the solutions and talk about competitive programming. So the plan of this club, if you wasn't here for the last year, we just basically learn how to solve problems. So I have a lot of lectures recorded where I discuss different algorithms which you can use in competitive programming. So some of them are theoretical, but some of them actually very useful in competitive programming. But if you learn algorithms, it's actually, even if you know a lot of algorithms, it will not guarantee that you solve problems well. So in this club we focus on problem solving skills. So what I'm doing basically, I prepare contests based off some random problems from Codeforces from different years, different topics. I try to make them as random as possible. So you learn how to solve any problem that judges throw at you. So this time we have a very specific problem set actually. So I like problem set for today, but it will not be like this every week. So every week we'll have something a little bit different. So you need to adjust every time. Okay. So I plan during this season add more thematical contests. So for some weeks we will have some specific topic. And so I will tell you in advance what topic we'll have, so you can prepare, so you can watch some lecture, prepare yourself to some specific topic, and then solve a few problems of various difficulty for the specific topic. But not today. First contest, we will just solve random problems and just get used to it. Okay? Is it okay if we didn't do the first contest? If you didn't vote, okay, so now I will discuss the problems of the first contest. So if you didn't solve it before, it kind of does make sense to discuss the solutions. So the idea is that the first you try to solve it by yourself and do as much as you can. So basically you spend these 3 hours or as many as you need to solve these problems. And if you didn't solve some problems, you can ask in the chat or we will discuss it here. So I will discuss my solutions. I will discuss some of your solutions. So that's this. So, but if you didn't solve this contest, it kind of doesn't make sense. You just listen to my solutions. It's not very useful just to learn other solutions. Yes, so the idea is to learn how to come up to solution by yourself. Yeah. So if you didn't try it, you will not learn it. Again, the idea is, so how do you learn how to solve problems? You basically learn you solve a lot of problems. That's the idea. So the more problems you solve, the better you are in solving problems. Yeah, and later, if you solve more and more problems, you will learn some similarities. So you will read the problem statement and see, okay, I had this structure in some another problem 2 years ago, and we use this idea there. So maybe I can use the same idea here. And sometimes it works, sometimes it doesn't work. So you will see. So later, and you kind of teach your neural network in your brain to some patterns, you know. So you see which approaches will give you the solutions to some problems, and then you combine these approaches to get the solution to the given problem. Yeah, so that's kind of the idea. So if you didn't try to solve it by yourself, it kind of doesn't make sense to listen to my solutions. Okay, so let's discuss the contest. Let me share the screen. Okay, so so today contest was not very hard, as you can see this result. So some people managed to solve it in an hour and a half, like hour 24 minutes. This is actually great result. I didn't expect it to be solved that fast actually. So either you are too smart for the green rating or the contest is too easy. Okay, so you just started, so probably you're just too smart. Okay, so you don't supposed to be green rating enough. Okay, so you're just underrated. So last problem was kind of tricky. Surprisingly, a lot of people solved last problem but didn't solve previous problem. I actually expected the last problem to be more difficult for you, but let's see. So the first problem was very easy actually. So it's just to start the contest. So you just need to read the problem statement and understand what's going on. So we have some children. We need to split them into 2 groups by the points. Yeah. So we have yeah. So we put some passing rate k, and we put students with lower points than k in one group and k and more points in another group. And we need to choose this passing rate such that both groups have size in range from x to y. So we have these ranges x and y. Yeah, and we need both groups to have sizes in this range. And the constraints are very small actually. So number of this m is up to 100. So you can basically check all possible split points. So you have 100 possible split points. For each point, you can check if it is good point or bad point. And you can even do it in n squared times, because n is up to 100. You can do it in n squared times. So you can check all possible split points. For every split point, you calculate size of the one group, size of another group, check that both the sizes are in the given range. And if it is, then you just output this point. Let me go pop. Right. So here on the left is the full solution basically. So we iterate all possible values of k. When we fix value of k, we know which students go to the left group, which students go to the right group. So we calculate sum of the left group, sum of the right group, and check that both sizes are in the given range. If they are both in the given range, we output the result. That's basically it. So nothing very interesting. This problem is, again, that's usually happening. So the first problem is just to start the contest. So it's not supposed to be challenging for you. Okay. So I believe almost all of you solved the first problem. I believe all of you solved the first problem. Okay, so you probably don't have any questions about the first problem. Okay, not all of you solved the first problem. Interesting. So let's see what can go wrong in the first problem. Okay, you have prefix sums. You can do prefix sums. Okay, in this problem constraints are small, so you don't use, you can just calculate some grid in brute force every time. But yes, you can use prefix sums. Okay, I use prof sums from the left and from the right. Okay, check if okay. So I go from left to right. If prefix sum is okay, so if left group is okay, I check if I is less than m minus 1 and not check, then continue. Looks okay actually. I think what happened, minimum of, why this? Why this? I plus 2 and m. Because I may be m minus 1 and then okay. Okay. I have you some plus minus 1 problem. Do you see the mistake? If the m was big, could we use prefix sum? Yes, we can do prefix sums. Yes, you don't actually need m log n. You can do it in linear time. Yes, I agree. So do you see the mistake in this solution? It actually looks okay. So again, you overcomplicate the solution. So somewhere you made some silly mistake. That's what usually happens. Yeah, because if your solution is overcomplicated, you may have some silly mistake. So you have prefix sums inclusive. Not the best way to do prefix sums. Normally you do prefix sums exclusive. So you start from 0, then every next prefix sum is 1. Okay. So your prefix sum of I is inclusive of all numbers from 0 to I. Okay, and right prefix sum also is inclusive. Yes, I equal I plus 1. And in the range from I minus 2. Okay.
Maybe the prefix sum array, like prefix sum 0 is not initialized, and in the first loop, he wrote like prefix sum I minus 1. Maybe that's the issue.
No, we initialize prefix sum as an initial array. See, so this is our initial array. So we copy it to both this prefix sum and suffix sum, and then from this array we go from left to right, make this plus ones. So we create an array of prefix sums. Yeah, you see. Let me write here. So what we're doing here, we have like array 1, 2, 4. Yeah, so we copy it to array prefix sums and then go from left to right and just make here we keep 1 because range from 1. Yeah, Here we have 3, and here we have 4 plus 7. So we can array like this. It's not the best way to do prefix sums, but
can I say it?
uh-huh.
What if I the never mind, there is a break. I actually
Yeah, I
didn't
have
see the
break
break.
here. Okay, let's see the test. Okay. Curious what might be the problem actually. Okay, makes sense. So this is the problem actually. So you don't do it like this. So if you plan to make so you need to make this cutting point at any position to m. You cannot do it m plus 1. So okay, makes sense. Let me but submit pop. So instead of doing this, you do this in range m minus 1, because if you want to assign I to m minus 1, then here you do yes. Okay, so you added this minimum because you felt that something goes wrong here. Yeah. Okay, you fixed your mistake in the wrong way. Okay, that's tricky part actually. Okay. Nice. Let's go to the next problem then. In the next problem we have in next problem we have we have n plates, and we want to put some cakes on this on these plates, and the question is what can be the maximum possible. So if you look at the minimum number of pieces, we want it to be maximized. Yeah, so we want to maximize the minimum number of pieces on each plate. And okay, so normally, okay, let me stop here. So normally, if you see maximize the minimum, you do binary search. It's just normal thing. But since here now all the numbers are small, so just 100, you don't need binary search. You can do just linear search and anything. Yeah. So I will implement it without binary search. But normally, if you have the same problem but with big values here, you can do it using binary search. Here I just do very simple algorithm. So okay, let me just write something here. So what I'm doing here, I have these n plates. I choose which of them will contain the first cake. So some of them contain first cake, like k, and some other will contain second cake, so n minus k. Yeah. So I put the first cake, like I have a pieces on these plates, and I will put second cake on these plates. Yeah. And if you just have one type of cake, you can just to maximize the minimum, you just spread it evenly. Yeah. So I will choose how many plates I use for the first cake and how many plates I use for the second cake. Now I will see. So if I take a pieces of cake and spread them evenly among the first k plates, the minimum will be a divided by k. Yeah. And for the second k, it will be divided by minus k. And then I just take maximum over all possible ways to do it. Boom. So here is the full solution. Okay, can you? Yeah. Stop. Okay, so here is the full solution of the second problem on the left. Yeah. So we iterate for all possible number of plates we use for the first cake. If we fix this number of plates, we know how many cakes we have, how many plates we have. So we can just divide and see what will be the minimum amount of cakes on each plate, and then we take maximum of all of them, and that's the result. Edit one binary search. Yes, it's possible to do binary search. It's actually good thinking. So normally in any other contest, if I see the maximize minimum or minimize maximum, I would immediately do binary search. But here, since it's first problem, probably it can be done easier. Okay, it's the same thing. Who did binary search? Let's find someone who did binary search. No. Okay. Oh, you did binary search. Well, that's nice. That's what that's what my normal solution. Yeah. So like the minimum maximum. Okay, why you call them B and E, begin and end? No, okay, why not? Okay, that's my way to implement binary search. So I have some good value, some bad value. So this is reachable value, this is unreachable value. Yeah, so I check if this difference is greater than 1, pick some middle value, x divided by amplitude. See here I see how many plates I can cover if I need to place at least m pieces of cake. Yeah, so I can cover this amount for the first cake and this amount for the second plate. Nice. So again, this solution is actually faster than mine. So here, so you see, so if you have the same problem with bigger constraints, you can use this approach. It will be just faster. But again, always you don't need to solve problem with the most optimal way. Yeah, you solve the problem in given constraints. Yeah. So if constraints are small, sometimes you can implement just more simple solution, and it will still pass all the tests. Problem C, the naive solution just iterate over all numbers, check if it's divisible, then you skip it. But it's obviously too slow, and because 10 power 18, it doesn't matter how optimal your solution is. 10 power 18 is just too much for anything. So it's just if you spend like nanosecond for each operation, it will several thousand years before you finish. Yeah. So 10 power 18 is definitely something you don't put in your for loop. Yeah. So you need something faster. And the way I do it is just very simple. So there are many ways to solve this problem, by the way. You can do it using Inclusion-Exclusion Principle, or actually many ways to do it. I do it using the period search. So I noticed that this sequence is obviously periodic with some small period. Yeah. So I care about the numbers divisible by numbers from 2 to 10. Yeah. So this divisibility function is periodic with the period equal to the lowest common multiple of this number. And like lowest common multiple of numbers from 2 to n should be kind of small. Yeah. So that's it. That's the whole solution. So if you have some periodic sequence, you can take the period, calculate your function for this period, and then repeat it multiple times. Yeah. You can do it just on paper actually. So you can find this lowest common multiple on paper. It would be something like, so it shouldn't be divisible by n of 2. So you just need to multiply primes. Yes, it's something like 2 by 3 by 7. Right? Yes. I think the period is something like 42, right?
No, 5. You didn't include 5.
5. Okay. So 210. Yeah.
Yep.
Okay. So the period small. So I'm here. Okay. So LCM is actually greater than the period. Yeah. Because I care only if they're divisible by or not. So if it's not divisible by 2, it's definitely not divisible by 4. So I can skip 4 and something like this. Yeah. So actual period is actually shorter than this, but again, this number is definitely period. It may be greater than period, but it's okay. Yeah. So now I just simply calculate the function, just using brute force, calculate the function for this period, because the period is small, numbers are small, so I can do it really fast. Yeah, basically check all the numbers. Yeah, so as the sum for the single period, here you need to place 2, not 1. I will fix it. Here I check the number n and remove all the whole periods. Yeah, so I take n divided by p is number of the whole periods. So I just take this number of whole periods and multiply it by the function for the single period. And this I calculate all the whole periods. And then I need to calculate the rest is just n modulo p. Yeah. And here I thought for a little if I need a function for this, but I decided to be lazy and just copy paste the code. It's not the best way to write the code. It's just to copy paste the same function 2 times. But If it's just 2 times, it's not as bad as it looks. And again, and here I find the mistake. Yeah, I need to replace this 1 with 2, and since I copy pasted it, I need to replace it in two places. So I need to replace it here and here. If you copy paste 10 times, you need to replace mistaken 10 positions. It's probably not what you want to do, but again, it's always about balancing. Okay, so I can put it in a function, but then you spend some time creating function, refactoring your code. Yeah, so it's always a trade-off, between the beauty of the code and the time you spend refactoring. Yeah. So I did it like this, and it's okay. And here I test just that I just make sure that I didn't make some silly mistakes. So I just remove this part which calculates the periods and just check if I have the same numbers with it and without it. Boom. Okay, that's all. That's it. Okay. Well, that's basically it. So that's my solution. It's not very short. I believe it can be done very much shorter, but it's okay. It's working. So that's it. That's problem D. Let's read some of you. Okay, that's another way to do it. So okay, here we have inclusion-exclusion formula. Okay, done on paper and just implemented. Why not? Why not? So basically, again, what is inclusion-exclusion formula if you never used it before? So what we have n numbers. When we remove numbers divisible by 2, numbers divisible by 3, divisible by 5, divisible by 7. Yeah. But if we do it like this, some numbers we remove twice. Yeah. For numbers divisible by 6, we removed 2 times, here and here. So we add them back. And also we add back numbers divisible by 2 and 5, 2 and 7, 3 and 7, 3 and 5, 3 and 7, and 5 and 7. Yeah. So all the pairs we return back. Now, if you look at triples, like numbers divisible by 2, 3, and 5, we removed them 3 times, and then we add them back. So you need to remove them back. So you remove all the triples back. I add and remove them. So I added them 3 times, and I moved this. So here. So I need to add them back. Yeah. So I add them back, and then you have numbers by all 4 of them. So so basically you subtract all the subsets of even size, and you add all the subsets of odd size. Yeah. So subsets of size 1, 3, and 5. 5. We have 5. 1, 2, 3, 4. No, we have 3, 4. It is 0. Okay. Doesn't matter. So we add everything of size of even size, remove everything of odd size. Okay. Okay, because because I need to, you need to calculate not all the divisible numbers, but non-divisible numbers. So it's opposite. So this is inclusion-exclusion formula, just in explicit way. Yeah, nice. Also nice way to solve this problem, actually. You can generalize it for bigger numbers of k, but you don't need to. You're given number 10 in the problem statement, so it's actually much faster than my solution. Yeah. Next problem D. I love problem D. So the main difficulty of problem D is to read problem statement. So problem statement is specifically very complicated. Yeah. So actually, this is kind of easy problem, but so easy not in terms of solution, but the statement is actually easy. But the formulations in the problem statement are specifically made overcomplicated just to scare you. Okay, so sometimes it happens. So sometimes let me open it here actually. So sometimes what problem authors do, they make a simple problem look like a hard problem. by using these strange formulas and strange mathematical constructions and so on. So let's just, so how do you read problems like this? You read them like you normally read problems. So you should just read what's happening and bit by bit understand what's going on. Yeah. So important part is you shouldn't be scared of the problem. Like problem should be scared of you. Okay, you are solving this problem. You're in charge. Yeah. So you just read the problem and just carefully understand what's going on. Yeah. So let's see. So what's happening here? So the most scary phrase is here. So neighboring color diversity for color K. So it's okay. It's immediately written like this just to make you scary. So they make special term neighboring colors diversity. Okay, because it sounds scary. Okay, so you just read this and think, okay, this is just some term. Okay, you can rename it to something like like beauty of the color, or something like so something not scary. Okay, so it's just some funny function or something like this. Yeah, so it's just okay. So this funny function is defined like this. So this funny function is defined for any color. Yeah, so you take a color and you define some funny function of this function. So function Q. Yeah, so function Q, what is it? No, the function of cardinality. Okay, function. It's not a function. It's set. Okay. Let's read it again. So we define this funny function of color K as cardinality of the set Q. Okay. Cardinality of the set is just number of elements in the set. It's just scary way to tell you number of elements. Yeah, just cardinality of the set. Okay. So we calculate number of elements in the set. What elements? What elements we have? Okay, so what elements we have in the set? We have some CU. CU is color. Yeah. So you go back to the definition. CU is just color. So it's cardinality of set of colors. Let's rephrase it to some simple way. So it's just number of colors. Okay. So function of the color is number of colors not equal to K. So for color K, we count how many colors not equal to K. There is a vertex V belonging to set VK. Okay, they use VK just to scare you. VK, you go back. So VK is just go backwards, vertex of color K. Yeah. So we look at all vertices colored with this color K, such that nodes V and U are connected by H. Okay, so we take some vertex colored with color K, then take some edge from V to U and look at the color of the vertex U. So let's rephrase it now. So this funny function we want to calculate is number of colors we can see if we take some of the vertex of our color and make some neighboring vertex. Yeah. So we take some neighbor of our color, yeah, and look at the color of this vertex. And this is just number of different colors we can get. Yeah. So basically it's number of different neighbors, number of different colors of the neighbors of the vertex of color K. Okay. So you just read read the sentence multiple times until you're not scared of it, until you understand what's going on here. Now, when you understand what's going on, it's actually doesn't look very scary. Yeah? So for every color, we need to calculate how many. Okay. Now, what we need to calculate for every color, we take all the nodes of the color K, look at all the neighbors, look at all the colors we have here other than K. So if they're connected, we're not counted. And among all these colors, we count how many different colors we have. Well, we can do it using simple sets in C++. Yeah? That's it. And then we need to find vertex, or find the color with maximal number of different neighboring colors. Sorry. That's it. So what I will do? Okay, I do it in a strange way. I just put this map. So for in this map S, for every color, I will count which other colors I have as neighbors. Yeah, here. So here, see. So I read the edge, and for every edge, I take to add ends of this edge and add this color to the corresponding sets. Yeah. So if I have edge connecting colors X and Y, I put X to the set of Y, Y to the set of X. Yeah. Now in the end, for every color, I have set of all neighboring colors. Okay, here I do something strange actually. Here I noticed that so the problem is that here in the last, I need to find the graph that I find the color which has at least one color which present my graph. So I need to find the color that at least one vertex have this color. So okay, I do it in a strange way here. Let me skip this. I rewrote it a couple of times. So I look at all colors here and check if the number of neighbors is greater than mine. Then I update my result. You also need to find the minimum. Yes. So I rewrote this like this. Also, I made another wrong answer because I didn't notice that. So in this map, I don't have empty set. So some colors do not have any neighbors. So I didn't put them in this set. But I need to process them. Not the best way to do it actually. Okay, so here I just put them in this set. So in this set S, I put all different colors. And here I later just process all of them. Not the best code actually. So here. So again, I put all different colors in this set S, in this set O. Now iterate over all possible colors, check if number of neighbors of this color is greater than number of my set, or if it is the same and the color is less than me. Yeah. Then I update my result. Don't like this code that much, but it is a working code. Okay, let's look at your solutions. Let's look somewhere here, and then we'll back. Okay, basically the same. Yeah, you have map of if it's different. No, okay, it's the same basically solution. How do you handle this situation? Like this. You have special case when you have 0. Yeah. Then the answer is 0. You need to output minimal color, so at least one node have this color. So you have minimal color of all your nodes. Yeah. So you handle it like this. Okay. I was hoping you have something more elegant here. No, that's an interesting way to do it. Interesting notation. So technically correct, but that looks funny. Has color, best color, angel, but with best color scheme. So you don't have this special case. Why? It has color. Okay. So you mark you mark all the colors that you have in your graph. Okay. It's another way to do it. So instead of having only colors given, you just have array of all possible colors. Yeah. And then you just mark the colors that you actually have in your graph. Makes sense. Problem is fun. So there are many problems like this. So basically, what's happening in this problem? You're given some so you're given some hidden number. So your rating, yeah. So your rating is some hidden number, and you're given some information about this hidden number. In this problem, we have two types of information. So we have this hidden number changed by some amounts. So we have this difference C, yeah? Difference D. No, C is difference change. Yeah? So sometimes we change the number by some delta, and sometimes we have some constraints on this number. So we in this problem we have the current rating of the participant. So we if the current division is 1, we know that the rating should be at least 190 or 1900. And if the division is 2, we know that the rating is at most 1899. Yeah. So we have these like constraints on the current value. Yeah. So what is the idea? Idea is to perform this operation and remember the possible values of the of your hidden number. So in this problem, so sometimes different. In this problem, your possible value of your rating is always some segment. So it's always some range between this and this. Why is it true? No, because again, if you play a little with this situation, what's happening? So initially you have all possible ratings available. Yeah. So then someone tells you if you're in the first division, let's say, okay, let's look at the first. Let's look at the first example. So in the first example, you see that you are in the first division. Yeah, it means your current rating is from 1900 to infinity. Yeah. So initially your rating was in this range. Then you have -7. Yeah. So after you apply -7, your possible rating will be in the range from 1893 to infinity. Then after this, you should be in the second division. Yeah. In the second division, it means that the highest rating you have is 1899. Yeah. So actually you have from 93 to 1899. Yeah. And then you must be then you apply +5. Yeah. Then you apply +5 to this, and then you have rating from 98 to 194. And then you must be in the second division. So again, you just cut this right part to so you have from 98 to 199. And then you apply +8, so you have, yeah, this is final result. It will be 9007. So again, idea is that your possible values belong to some segment. Yeah. Because operations you do are just cut something from the right, cut something from the left, and move left to right. Yeah. So always maintain some segment of possible values. And okay. The only trick is sometimes you have right border to infinity. Yeah. So yeah. So I do it like this. I put the range from -billion to +billion. Billion should be enough. I just check that I have 200,000 changes, each change up to 100. So it's like 2 by 10 power 1, 2, 3, 4, 5, 6, 7. Yeah. So up to 200 million. So billion should be enough. Yeah. So I check which division I'm in. Okay. So here I misplaced C and D. So if I'm in the first division, I move the left border to 1900. If I in the second division, I put right border here, and then I just move my current segment to this delta, and then I check that it is impossible. So I check that my segment is non-empty. If it's empty, I check the right border is infinity. Okay, I do it like this. So if it was billion, I didn't move it up to half of the billion. So I check if it's still greater than half of the billion, then it's still in an infinity. Yeah. Okay, not the most clean way to do it, but good enough. Okay. Here I forgot to read n. It happens every time. That's the whole solution of this problem. How do you think about this problem in terms of non-algorithmic but mathematical way? Okay, I'm not a mathematician, so I'm not sure I understand how mathematicians think. But what's happening in this problem? So you have some, basically you have some linear transformations. You have just shift linear transformations. And you have some constraints. And every constraint is just, again, some linear constraints. So we have linear transformations and linear constraints. So the result should be linear function in this way. Yeah. Again, if problem is one-dimensional, so it must be a segment in some sense. Basically, if you have some number x, then after we apply some operations, the current, so if the initial values will be x0, so it's initial rating. Yeah, then my current rating like xi will be x0 plus all these changes, plus c0 plus c1 plus and so on plus ci minus 1. Okay. Yeah. So it will be initial rating plus some shift. And you have constraint. Basically, you have like something like xi greater or equal than 1900. Yeah. Yeah. So you can translate this constraint to the initial rating. So instead of having this, so this part should be greater or equal limit. Yeah. So you can move these elements to the right and see that x0 should be greater or equal than 1900 minus this sum. That's how I usually think about problems like this. So I I have just one unknown variable. So in my problem, I have one unknown variable, it's initial rating. If I know the initial rating, I know all the everything what will happen next. Yeah. So I have this one unknown variable. So I treat all the constraints I have later as constraint on my initial rating. Yeah, like this. Yeah. And see that they are all very simple constraints. So I just combine all of them. And again, if you have constraints greater or equal something, they just say that your value is somewhere here, and constraints less or equal something. Yeah. Then if you want to combine all these constraints, you need to find greater of all of this, smaller of all of this, and here are your possible solutions. Yeah. Okay, let's see. Let's read some of your solutions, maybe. Okay, let's read you. How do you solve it that fast? You must be really smart, much smarter than me. Okay. Okay, you calculate the total change here. Why not? Low, high, it's not. Okay, so see here you maintain these infinities because you can. Okay, I used more lazy approach. I just move these infinities and just make sure they don't move too far. But that's more safe approach. I agree. But why you go around to it? Okay, so basically doing the same thing but doing right to left. Why not? So you start from the final rating and go backwards. Look, sometimes it's just easier to think in this way. Okay, but again, the problem is fully reversible. So you can do it left to right or right to left. All these operations are basically reversible. Yeah. Okay, then in the end, you need to add this sum back. Okay. Why not? Okay. So that's one variant of the classical problem when you need to put some numbers and make sure that the consecutive numbers are different. The idea is that here I'm just drawing something to find what is the easiest way to solve this specific problem. Again, so we have some numbers. We need to put them in a cycle in such a way that consecutive numbers are different. many ways to do it actually. So the approach I'm using is the following. Let me see. So you can do it like this. So you have some numbers. So what can you do? For example, you can pick just two numbers and try to alternate between them. And then if you run out of numbers, you pick some another number and alternate between them, and so on. It's doable, but just overcomplicated. Instead, what I will do, I will take one number. It's number. What color? What is it? So what? A picture gallery from the same. So pictures from the same album. Okay, doesn't matter. Pick some number. So I pick some number and put it at as many positions as possible. Yeah. So pick number one. I have a lot of numbers one. Imagine. Yeah. So I put as many of them here. So I can put them every second number. I put number one. Then you take some another number and put it in all remaining positions and so on. If you have odd number of elements, let's put 5. Okay, let's put 7 elements. Yeah, you can do it like this. You start from some element, put it here, then you move 2 positions forward, put element here, then you put 2 positions forward, move here. Yeah, that's it. So you can add at most 3 elements. Now you take the next color and you start from this position. Boom, 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 boom. So I just will put my elements in this order. I put element here, then here, then here, then here, then here, then here, then here. And if I put no more than 3 elements of the same color, I will never put 2 elements in the same place. Yeah. So again, I can put elements like this. I can put like A, then B, and then C, something like this. Yeah. Yeah. So I take this element. I take all possible colors, sort them by the number of elements that come. Then I put these elements in this order. So I put this A, then A, then A. Then I take B and B. A. Then I put B and B. Then I put C and C. Yeah. And if I don't have more than 3 elements of the same color, I will never put two neighboring elements of the same color. So that's the idea. So instead of trying to alternate between 2 colors, I just take one color and put as many as possible, and then continue to the next color, put as many as possible. Yeah. Okay. So here I'm just Here I take the minimum of AI and n divided by 2. So I cannot put more elements than n divided by 2. Yeah. If I put more than n divided by 2, I will put 2 in this in consecutive positions. I don't want to do it. Yeah. So again, here I do it like this, and then I put them in all. Now I need to sort it, but I forgot to sort it. I will sort this array C. Now, if total number of elements less than n, it's impossible. Now, I have some elements, total number of elements greater than n, and every element is not greater than n divided by 2. So I just go and put them one by one in with step 2. So I start from position 0 and then move it 2 positions forward every time and just put all my elements in these positions. Okay. 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 Here I'm doing it in difficult ways actually. So here my array C contains pair number of elements and element. So I skip all empty elements here and then take one first non-empty position. Yeah. Do you know easier solution for this? It probably can be done much easier, but okay.
Maybe by coloring.
What do you mean by coloring?
Like constructing a bipartite graph. I don't know the full implementation, but I think it can be solved like that.
Again, it's not bipartite if you have if the n is odd, it's not bipartite. Okay, it's not that bad implementation. It's not the greatest, but it's working. So okay, let me show you the full code. From here, where is it? Let me actually copy it to the. So what I'm doing again, let's read it once again. So I'm reading all the colors here. I just put them in this array C for sorting. Yeah. So for sorting, I put the array C number of elements and the color. Yeah. So I is the color. AI is number of elements of this color. Number of photos from this album. Yeah. And I decrease the number to n divided by 2. If number of photos is greater than n over 2, I make it equal to n over 2 because I cannot put more than n over 2 photos of the same type. Yeah. Calculate the sum. If sum is less than n, immediately impossible. If it's greater than n, always possible because I do it like this. I start with position 0 and then every time make +2. With only exception here, because if number is even, okay, here. If the number is even, like so you start from some position, you go here, then you go here, then you go to the cycle. Instead of going to the cycle, I go to this position and then go here. Yeah, like this. 1, 2, 3, and then 4, 5, 6. And again, I never take two consecutive elements of the same type except in the end. So after 6 and 1 should be also of different type, but they will be on different type because it's first last element. 2, 2, 2. So here, I find the first non-empty group of photos. Yeah, sorry. So J is my leftmost pointer to the first non-empty group. I skip all empty groups, then take, okay, actually I sorted them, so they shouldn't be more than, okay, that doesn't matter, so it works, yeah. So I skipped empty group, then take one photo from some non-empty group. So first is number of photos, so I decrease it by 1, and put it to this position. Yeah. So first I will put all first photos, then all second photos, and so on. Okay, hope it's clear enough. Let's read some of your solutions. Okay, you're the first one. Let's. Oh, it's actually shorter than mine. Let's read. Okay, so let us start to find mem spread by this will be spread by 2 to n. Choose. What? Okay, so I choose the maximum, yes? So if choose is less than me and j is not so I choose the maximal element not equal to the previously added element. Just greedily do it. Okay, why not? So just every time you put the element with which the largest element which is not equal to your neighbors. And this greedy approach will give you, so if it's possible to construct, then you will construct. No, makes sense, yes. No, because again, the invariant is every element can be more than n over 2 times. And if you decrease only the maximal element, then you just maintain this invariant. Okay, nice solution. It's actually shorter than mine. It's harder to prove actually. But if you believe your solution works, yeah, why not? And also you iterate over the start element because you don't know where to start. Okay. So it's right of the first element and then add the element greedily. Nice. Problem G. Oh, problem G is mathematical problem. So in problem G, we need to put some brackets in the sequence of implications. So we have these implications, and yeah, we need to put some brackets to make the whole formula equal to 0. Nice problem. So no special algorithm needed. You just need to investigate what's going on. Yeah. So let's investigate. First, let's see. So to get 0 in the end, we need to have the final implication should be 1 to 0. Yeah. So you see, to get 0, you kind of need to have 0 before. Yeah. So if in the end you have 0, then in the last implications you have 1 to 0. Yeah. And again, how did you get this 0? When you need to get this 0, you had something like 1 to 0 before. Yeah. So every time the last element is 0, you cannot get rid of this 0. Yeah. Or you can think in the opposite way. You cannot get rid of 1. So if you have some sequence, something, and last element is 1, then no matter what you do, the last element will always be 1. Yeah. So what I'm doing here, I try to find some invariant of this sequence. Yeah. So I see I'm trying to find some value which doesn't change when I apply this operation. For example, I'm doing just by playing with this model. So I just look at this model, try to do something, and see some patterns. Yeah. So I click, for example, if I have 1 in the end, then no matter what I do, so I have this 1. If I have like 0 to 1, yes, again it's converted to 1. If I have 1 to 1, again it's converted to 1. So last element will always be 1, no matter what you do. So if you have sequence something 1, it's impossible to make it 0. Okay, we solved already some cases. So now we only care about case when the last element is 0. Now you think, okay, last element is 0. Now, to make the final result equal to 0, I just need to, from this, get some 1. Yeah. You think, okay, I need to get 1 from this part of the sequence. Okay, I know how to get 1. So if this element is 1, it's very easy. I do anything here and I get 1. Yeah. So let's mark all the cases which we know how to solve. So we now solve case if last element is 1. That's impossible. Yeah. Record posting record. Yes, we will post everything. Yes. If the last element is 0 and this element is 1, then it's easy. So easy. Yeah. You just do anything basically. So you just combine these to 1 and then you have 0. Now if the last element is 0 and this element is 0, that's interesting. Yes. Now you need to get 1 from this somehow. How did you get 1 from 0? To get 1 from 0, you look at this again. Look at this formula. So you need to get 0 to 0. So I need to get another 0. Yeah. So I have 0, but I need to have 1 in the end. Yeah. So I need to have 0 to 0. If you have another 0 here, then it's okay. Yeah. I combine this, get 1. Then I do anything again. Okay, that's easy. If I have again, what I'm doing, I trying to find all the cases that are solvable, and then reduce my problem to smaller and smaller set of cases. Yeah. So I already solved a lot of cases actually. So and if I have 0 and 0 and then have 1. Then here somehow I need to get, so from this part somehow I need to get 1. But 1 to 0 is 0. Yeah. So again, if I have situation like a lot of 1s here, it's impossible to get 1 here. Because 1s will always get 1 and 1 to 0 will always get 0. So again, it's impossible. And finally, I have case when I have 0, 0, some number of 1s, and then I have 0, and then something. Yeah. Then I just need to get 1 from this situation. Oh, it's easy. So you combine these, get 1. You combine these, get 0. And then you combine these, get 1. Yeah. So, yeah, so this case is impossible. This case is possible. This case is possible. This is impossible. This is possible. Yeah. And now we're out of cases. So we solved all possible cases. Again, we look at the last number. If it is 1, we're done. If it is 0, look at the previous. If it is 1, we're done. If it is 0, 0, look at the third number. If it is 0, we're done. If it is 0, 0, 1, then we look at the rest. If it's all ones, we're done. If it's not all ones, then we have some 0 here, and we're done. Yeah. So you just get rid of the cases one by one. Yeah? And just hope it will not be too many cases. Yeah. Solved it. Oh, you solved it without this case. That's fun. How did you do it? Okay. It's interesting. So you have less cases than me. Here I'm thinking. Again, this is my recording, so we'll skip this part. Okay, here I will just... Also, you need to output the result. That's another fun part of this problem is you need to output the result. So here I try to do it as simple as possible. So if I have 0, 1, I just output as it is without any brackets, because you can implement from left to right, and you're done. So here I find the position of this 0. So this position is J. Yeah, see? Here. And yeah. Okay, here I'm thinking what's the way to do it. Yeah. So I will just write all this thing and just put these brackets in corresponding positions. So I just draw here where I need to put brackets. So I need to put 1 bracket here, 2 brackets here, 1 bracket here, and 2 brackets here. And now we just test that it works. These examples are pretty stupid today. So again, here I made some. So the most tricky case is the last case when I have 0, 0, and then something here. So I just check if in this case I output something that looks correct. Yeah. Again, combine these ones to 1. 1 to 0 is 0. 0 to 0 is 1, and so looks okay. Yeah. Then I get wrong answer. Okay, I get wrong answer. So I tried other cases. Yeah. Okay, and here I noticed something strange. So if I have 0, 0, 0, I didn't process in a separate case here, but I should. Yeah, because you have something like this, it doesn't work if you have just zeros. So I added another case here when I have 3 zeros in the end, like this. Okay, so that's it. That's solution for problem G. Sometimes problems can be solved like this. You just track all the cases that you know how to solve. You think, okay, this case I know how to solve, this case I know how to solve, this case I know how to solve, and then something rests. So maybe somewhere in the end you need to use some specific algorithm. So you get rid of all stupid cases. In the end, you have some, let's say you solve problem for this, and then you have some bipartite graph, and you apply some bipartite matching, or you get rid of all stupid cases, and then you have only a case when n is, for example, if n is even, it's easy to solve. So you only stack with cases n is odd. When n is odd, you do something interesting. Yeah. So you remove all non-interesting cases and then see what's left. In this problem, nothing left. So I just get rid of all cases and nothing left. So sometimes it's just like this. You just track all the cases until you have no cases left. Sometimes you have some core in the end, and then you solve this core problem using some interesting algorithm, but not here. Okay, let's review again. Your fastest solution for this problem. Okay, nothing very fine. Okay, so again, so just track different cases here. Okay. Does anyone have anything smarter than this? No, it looks the same. It looks the same. Just do this print in different way. Okay, I believe it's actually the easiest solution for this problem. Just to track all these cases one by one. So in problem H, what do we have? We have 2n chairs. We have 2n people. Yeah, some of them are boyfriends and girlfriends. So we have pairs. Yeah, so we have some pairs of people are sitting in some chairs. So we know the position of the first, position last. And we need to assign some dishes to them. So we have 2 types of foods. We need to assign to each person some type, 1 or 2. And we have constraints so that people in the same pair should have different types of dishes. And we have this strange constraint. This constraint said for any 3 consecutive guests, we should have 2 different types of food. Okay, so this constraint looks strange. So we'll look at it more carefully. Again, we have some people sitting around the table. Let's say 1, 2, 3. Let's see, it's odd. Let's say 8 people. So we have 1, 2, 3, 4. 1, 2, 3, 4. And they are split it into pairs. Let's say we have A and A here. So A and A are from the same pair. Yeah. So we have these 2 are in pair, these 2 are in pair, and let's say these 2 are in pair and these 2 in pair. Yeah. So I want to assign each of them type 1 or 2, and so the first constraint is that the people of the same group, of the same pair, should have different. So this should be not equal to this should be not equal to this, not equal to this, and this should be not equal to this. Yeah? So people from the same pair should get different types of dishes. Now, the second constraint is more interesting. Second constraint is like this. It says that for every 3 consecutive, so if I look at this 3 consecutive numbers, then among them I should have 2 different types of food. Strange constraint. So let's rephrase it in more simple way. It means it's impossible to put 3 equal values in a row. Yeah. So it's possible to be 1, 1, 1. Yeah. Or 2, 2, and 2. Yeah. So you never can see three elements of the same type in a row. Yeah. You can, again, so the sequence should be something like this. So 1, 1, 1, 2, 2, 1, 2, 2, 1, 1, 2, something like this. Okay. You never see 3 elements of the same type. Maximum you have 2 elements of the type. And the question is to find the arrangement that corresponds to these parameters. Okay, I'm surprised a lot of people solve this problem that fast, because I find this idea kind of challenging. So, first of all, how do you approach problems like this? First of all, what you see, how I usually do this. So, first of all, I think about situations when the answer is impossible. So, sometimes the question is, if there's no solution, print -1. So I immediately start to think when it's impossible. So what is the condition when it's impossible? Try to find the example when it's impossible. And again, if you play a little bit with this model, you will probably find that it's hard to find example when the answer is -1. And also you will see that in the given examples, there is no example of -1. So there is no example when the answer is impossible. And again, if you play a little, you will not find this example by hand. Yeah, usually it means that this situation just doesn't exist. So when there is no example with impossible, and you cannot easily find an example when it's possible, usually it means that it just doesn't exist. That the answer is always possible. It's just a hint. If you see situations like this in future, so if there is no example for -1, probably -1 just doesn't exist. Not always, but most probably. Now you think, okay, why it's always possible? Again, now when you know, okay, when you guess, okay, the solution is always possible, you think, why the hell it's always possible? Yeah, and you think in this direction. You think in direction from the position when the solution exists. So you know the solution exists. You just know how. You just think how to find it. Okay. Now the next step I made is to rephrase this second constraint. The second constraint is strange. So he's saying that among any three numbers, at least two are different. Strange constraint. Yeah. I already have the first constraint that says that two numbers are not equal. So I try to rephrase the second constraint in the same way. Yeah. So you can rephrase it like this. If you pick three consecutive numbers, then either these are not equal or these are not equal. Yeah. So if you pick any three positions, then one of these pairs should be not equal. You can't have equal and equal. Yeah. Again, I try to rephrase the second constraint in the same way as the first constraint. So I have kind of the same types of constraints. So it's easier to combine them. Okay. Now I think, okay, I have some constraints about some non-equality. Some elements are not equal. Yeah. And you can do it if your graph is bipartite, like you may probably know. So I try to find some bipartite graph of this. So again, so I know this A and A should be not equal. I know this B and B should be not equal. No, the C should be equal. Yeah. So I need to add some another constraints that may give me a bipartite graph. And also make sure that at least among all pairs, at least two consecutive from two consecutive elements, at least one is not equal. Yeah. So you think about, okay, so I can just alternate. I can make these elements not equal, these elements not equal, these elements and these elements not equal. Yeah. So I just go one by one and split all elements into paro consecutive elements and say that these elements should be not equal, these elements should be not equal, these elements should be equal. Or you can think like this. Another way to do it is like so. Just try to build a solution. So okay, I guess the solution exists. Yeah. So I try to build it. Let's pick this A. Put something here. So it's A should be 1 or 2. Let's put 1, for example, here. Then this should be 2. Yeah. Then one of the neighbors of 2 should be 1. I can't have 2 and 2 here. Yeah. So at least one of these neighbors should be 1. Let's pick, for example, this neighbor. Let's put 1. Yeah. Then corresponding here should be 2. And so on. So now I have kind of cycle here, you see? So I put 1, 2, 1, 2, and I'm in a cycle. And then you get another element again, put 1, 2. Here you have 1, here you have 2, and I have another cycle. And I think, okay, is it always possible to split my elements into cycles like this? And you see, okay, yes, it's actually always possible if I just alternate these edges here on the boundary of this cycle. Yeah. Then I will get some number of cycles, and all the cycles have even length. See? Okay, hope it's clear enough. Okay, maybe you tell me how did you get this solution that fast? Because for me it was kind of tricky idea that you can do it like this. Okay, let's so here. After you get this idea, the solution itself is kind of easy. So yeah, I just do it simply. I just build the graph and make a bipartite coloring of this graph, just in standard way. Okay, let's copy the solution from here actually. Oop. I'll just copy my solution. So here I'm reading the input and creating the graph. I usually create graph like this, just vector of vectors, so it's a list of edges connected to the vertex. Here I add this edge from x to y, and here I add all these edges on the boundary of this cycle. Yeah. And here I just go and mark, just color everything in two colors. I assign color -1 and then use DFS to color everything. So this DFS, so it's just general GFS. I don't think about cycles. I just color them as bipartite graphs, because even cycle is bipartite graph. Yeah. So I just use standard algorithm for coloring. So I just take this number and color it, then take all the neighbors, color it in color 1 minus c. Yeah, so 0 is 1, 1 is 0. No, that's it. That's the whole solution of my last problem. Let's look at your solutions again. 28 minutes. How you do it that fast? So again, you go from here to here in like 15 minutes. You're very smart. Okay, it's basically the same solution. Yeah, you build this graph, and here you color them as a bipartite graph. Good for you. Good for you. I cannot do it that fast. Okay, you do the coloring using breadth first search, not depth first search. Why not? Why not? Still possible. Okay, you go left, right. If it is not colored, then you color it using BFS. Let's see some incorrect solutions. Constructive bipartite graph coloring. Good start, but why it's not correct? Wrong answer. Oh, sorry, wrong answer. Okay, interesting. How did you get wrong answer? Yes, so we get these colors, or we get edges, we get these edges. What can go wrong? Did you make a mistake in this part? How did you get mistake in this part? This part is easy. It's just bipartite coloring. It should be done easily. So you can make Q push 1. Ah, you do it only once for vertex 1. So you color only single connect component. Let me fix it for you. Let me fix it for you really fast. So not like this. So we need to color all connect components. Yeah. So for int equal 1 s equal n 2n s plus plus. I do q push s and blue s this s. So let's say if already visited, I will continue. Yeah. And just do all this. Yeah. Yes, I believe this will solve our problem. Yeah. So I just do it not only from one, but for any unvisited node. No, yes, it will pass. Very close, very close. The way you handle situation, so how much you time? Okay, you had a lot of time actually. So you submitted it in hours, so you have more than an hour to find this mistake. Just don't be scared. If you have mistake, just try to find it. Yeah. Just run into multiple tests. Make stress tests if you need. Okay, you had a lot of time to find that mistake. Just don't stop. So if you stuck at a problem like this, just again find the test which is not working. In your case, it was very simple mistake, so you can easily find it. I encourage all of you to find mistakes like this. So if when you're stuck in a situation like this, just don't panic. Just find the mistake. Same thing here, only one DFS. Yeah, but overall good for you. So a lot of people solved a lot of problems. So it's, you all should be proud of yourself. Don't be hard on yourself. We don't always perform at the best as we can. Sometimes my performance is terrible. If you look at my rating, that it goes only down for a couple of times. Okay, so it's gone only down and down and down. Okay. Yeah. You just relax. Okay, it will never it will not be bad always. So sometimes you will get better. So just continue training and you will be all right. Okay, see you next week.